principle of a centrifugal pump can be seen here. Rotation of the impeller causes any liquid contained in it to flow towards the periphery because of the centrifugal force generated. The center or eye of the impeller is thus evacuated, and liquid from the suction line then flows in to fill the void. The cargo pump is supported by a deck trunk welded to the deck. All the connections are on the top cover plate, to which a capacity control valve is also mounted for remote and local operation of the cargo pump. This specially developed control valve regulates hydraulic pressure and oil flow to the motor according to the given discharge situation. The pressure gauge indicates the oil pressure to the motor. The pipe stack connects the pump unit to the top cover plate. Click on the components below to learn more about the pipe stack. The return from the cofferdam pipe. If any leakages, this will be discovered in the exhaust trap on the top cover plate during purging. This is the supply line for the cargo pump. It carries the oil from the power packs to drive the hydraulic motor. This is the return line for the cargo pump. It carries the oil back after it has been used to run the motor. Nitrogen or air is introduced during purging in order to ensure that the cofferdam is open and does not contain any cargo or oil. Cargo is forced through this line when the motor and impeller are running. When emptying a tank, nitrogen or air is introduced through the cargo discharge pipe, and any final remaining product is forced up this line and on through the cargo manifold. This is done to ensure that the tank and pump are cleared to the maximum possible extent on completion of the discharge. The cargo pump is running during stripping. The pump unit is mounted to the pipe stack/casing with a compact hydraulic motor located inside the casing. The motor is surrounded by low-pressure hydraulic oil. A short independent shaft, supported by bearings lubricated by hydraulic oil, is connected to a single-stage end-suction centrifugal pump. The hydraulic section is surrounded by a cofferdam that completely segregates the hydraulic oil from the cargo, with a manual seal condition monitoring system. This seal arrangement consists of a mechanical oil seal, single cofferdam lip seal, and a double cargo lip seal. The cargo seal is exposed only to static head from the cargo. Any leakages in the cofferdam chamber will, by purging with compressed air or nitrogen, be blown through the cofferdam check pipe and collected in the exhaust trap. A backstop unit is fitted to the shaft, enabling cargo to be loaded through the pump. Wearings are fitted between the impeller and the volute casing. Click on the buttons to learn more about the pump unit. The hydraulic system is built as a central hydraulic main ring line system in either a closed or open loop. Hydraulic pumps deliver oil to the main pressure line. From this main pressure line, a number of hydraulic motors can be run, provided that a sufficient number of power packs have been started. In order not to overspeed the hydraulic motors, a speed control valve is installed upstream of each motor. It is important to understand that the power packs deliver the oil and the cargo pumps are consumers. In an open-loop system, the hydraulic oil is gravitated from a hydraulic oil tank to the power packs, and further on via high-pressure lines to the cargo pumps and other consumers in the system. After use, the oil is transported via the return lines back into the hydraulic tank. A pilot line is installed to each capacity control valve in order to remotely operate the cargo pump from the cargo control room. An oil cooler is installed in the system in order to keep the oil temperature within desired limits. A jockey pump is installed inside the hydraulic oil tank in order to maintain positive pressure in the hydraulic system and to avoid contamination of the oil with cargo if a leakage should occur in the cargo pump. The jockey pump also serves as a cooling/lubrication pump for the main hydraulic pumps. This system requires a rather large hydraulic oil tank, since all oil used is returned to this tank before pumped back again to the consumers. Due to this, the open-loop arrangement is commonly used in small systems, while the closed-loop arrangement is preferred for large systems. Advantages include simple air release procedure, less piping, leading to cost reduction and lower risk of leakage, and a reduced number of components. The disadvantage of this system is the size of the hydraulic tank. In a closed-loop system, the hydraulic oil is fed by a feed pump to the power packs and further on via high-pressure lines to the cargo pumps and other consumers in the system. After use, the oil is transported via the return line. In a closed system, only 10% of the oil goes back to the hydraulic tank, while the rest is used directly on the power packs and back to the consumers. A pilot line is installed to each capacity control valve in order to remotely operate the cargo pump from the cargo control room. An oil cooler is installed in the system in order to keep the oil temperature within desired limits. 3 feed pumps are installed on the hydraulic tank, 1 running constantly, 1 in standby mode, and 1 in reserve. When the cargo system is not in use, the selected feed pump is delivering low pressure, sufficient to maintain positive pressure in the hydraulic system and to avoid contamination of the oil with cargo if a leakage should occur in the cargo pump. When the system is in use, the second feed pump starts automatically, increasing the pressure such that, in addition to leak prevention, 10% of the total oil capacity is returned to the hydraulic tank. The third pump is brought online in the event of a problem with one of the regular pumps. Since only 10% of the oil used is returned to the hydraulic tank, this system requires a much smaller hydraulic oil tank than the open system. The closed-loop system is commonly used in big systems. The advantage of this system is the size of the hydraulic tank. Disadvantages include a more complex air release procedure, more piping, and more components. Note: in the older systems, 2 feed pumps were installed. 1 was running in standby and 2 during normal operation. Hydraulic pumps, motors and controls are devices requiring close tolerances, controlled wear surfaces, accurate finish and an adequate supply of clean hydraulic fluid. Contaminated oil will not provide proper lubrication and is a leading contributor to reduced efficiency, excessive downtime and increased maintenance cost. The maximum recommended water content is 300 parts per million, or 0.03%, and must under no circumstances be above 500 parts per million, or 0.05%. If in doubt, please contact Framo. Recommended cleanliness level is code 16/12, according to ISO 4406, or CTOP PR20. 16/12 means that the number of particles above 5 micron in 1 milliliter is between 320 and 640, and the number of particles above 15 micron in 1 milliliter is between 20 and 40. The recommended operating temperature of the hydraulic oil is between 30 and 55 degrees Celsius. If the oil temperature is below 20 degrees Celsius, circulate the oil through the heating and venting valve installed in the system for heating with only 1 power pack running until the desired oil temperature is reached. Note: do not exceed 100 bar circulating pressure during heating. Even though most operations which happen when you push the start button on a power pack are automatic, it is important to know what actually happens and which items need to be checked prior to startup. In order to perform an economical discharge and minimize wear and tear on the equipment, it is very important that the number of power packs used corresponds to the number of hydraulic motors used. As previously mentioned, it is important to understand that the various pumps used in the system are consumers, while the power packs are in the delivery business. This means that one pump requires an amount of oil in order to operate, and the power pack has to supply the amount needed. In your manual on board, you will find a table where you can find out how much oil flow each hydraulic motor needs and how much oil flow each power pack delivers. See under Technical Data in your manual. When planning a discharge, just add the oil consumption of the number of pumps to be used at the same time and choose number of power packs so the flow delivered is a little above the flow required. For example, during discharging you will use 2 SD300 pumps and 1 ballast pump. How many power packs need to be run? The consumption of an SD300 pump is 938 litres per minute. 2 pumps will therefore together require 1,876 litres per minute. The ballast pump consumes 246 litres per minute. This gives a total oil consumption of 2,122 litres per minute. A small power pack delivers 697 litres per minute. 2 small packs will therefore together deliver 1,394 litres per minute. One big power pack will deliver 831 litres per minute. These units will deliver a total of 2,225 litres per minute. We therefore need to run 2 small and 1 big power pack to meet the demand. Before starting the main power packs, check the following. Hydraulic system tank oil level. That the cooling pump for hydraulic oil cooler is running. That the cooling fan for power packs is running. That the necessary number of generators is running. That the potentiometer for system pressure is in minimum position. That the speed control valves for all consumers are in minimum position. That the cargo pump cofferdams are purged. Start the main power packs. After an operation is completed, all consumers have been stopped and the main power packs are no longer required, the system should be stopped as follows. Reduce the hydraulic system pressure to minimum. Stop the main power packs. Stop the cooling water pump and fan. Stop the excess generator sets. Stop the feed pump and restart in low speed. This happens automatically after approximately 10 minutes. Always leave one of the feed or jockey pumps running in low speed to maintain overpressure in the hydraulic system. If by accident cargo should leak into the hydraulic oil system when the power packs are stopped, the mixture of oil and cargo would ruin the plant. To prevent this, the hydraulic oil pressure must always be higher than the cargo static pressure. When the hydraulic system is not in operation, one of the feed pumps will keep a hydraulic pressure of approximately 4 bar. One of the feed or jockey pumps must always be running in low speed, and all valves in the main return line and in front of all cargo pumps and other consumers must be open. It is important that emergency stop buttons are used in emergency situations only, and not for routine operational stopping of the system. An emergency stop stresses the system and should be avoided, except in critical circumstances. Emergency stop buttons should be activated when the following conditions occur. Damage to the hydraulic pressure pipes or hoses that leads to leakage. Critical pressure pulsation in the system, known as hunting. Critical vibration on the power packs. Damage to the cargo lines. Uncontrolled spill or leakage during discharging. The following conditions should lead to automatic shutdown of the system. Low oil level in tank. Closed valve in return line. Enclosed system low feed pressure. Enclosed systems feed pump failure when running at high speed. After a shutdown, the error must be located and repaired before restart. Before restart, reset system. Refill oil if necessary in accordance with normal procedures. Vent the system thoroughly and start up in accordance with normal procedures.